All right, infinite series. Now, just from that title alone, if this does not sound like a party to you, then man, you and I are more different than you thought. Actually, that's probably good news. Anyway, infinite series is what's coming up next, and this section, I make this little admission here. Oh, you know what? Before I spill the beans on that, remember that when you come to class, first of all, there's going to be a do now follow up from 8.4. We learned in the last video. I'll ask you some questions. You should be ready to go on that. And then this video has a comma right there where there should be a one. Has questions about what is the content of this video, which you should be able to discuss with your group, and I'll do the card call out thing on these 4 questions. So if you want to pause this now or come back to it, we're right around a minute in. You can come back and look and see what these questions are you're supposed to be able to answer after watching this video. Okay, man, there's a lot of traffic in my neighborhood tonight. Anyway, okay, so here's infinite series. I've already said here, and I make this little disclaimer right here. This is some pretty heavy stuff right here, infinite series. And actually 8.2, if you didn't notice, was kind of heavy too. These are the 2 sections that have to do with limits, 8.2 and 8.5. And really, by the end of this chapter, we're going to look back and I go to make the tests and stuff. 8.2 and 8.5 are going to be kind of light. Notice I did 8.2 on a day when I also did 8.3. Doing 8.5 kind of right after a quiz combined with catching up on 8.4. So already they're being slighted in the time frame. I just kind of want to give you an idea about what a limit is, and infinite series kind of takes it up one more notch. It's neatly right there in our book, so it's a good time to talk about limits. And like I've been saying, limits is one of those ideas that makes you sound like you know something about calculus. And really that's how the definition of what calculus is. It starts with the definition of limits. And the fundamental theorem of calculus is all about limits and derivatives and that kind of thing. All are based in limits. So I think it's good to send you off with a good dose of limits discussion, but at the same time, I'm not gonna dock you heavily on the test if limits are the one thing that escape you. Okay, so after having said that, let's pretend I didn't say that, because I am still going to talk about limits. Okay, so infinite series. We were just talking about in 8.4 and 8.3 about adding up sections of sequences, the first so many of them, adding it up and getting a sum of that. Well, what if we added them all up? And remember, the a sub n, generally speaking, goes on forever. If we add them all up, we're talking about, instead of talking about s sub n, we're actually talking about s sub infinity. Like, that just sounds like some playground made-up term. Like, oh, well, yeah, well, how about s sub infinity? Like, I know you are, but what am I? I know you are, but what am I? Infinity. Okay, so this would be like adding up. Let's get a sequence, and let's get an easy one. You know what? I keep coming back to this one. I don't know. I have a soft spot for this sequence. I don't know what it is. It's the +9 sequence starting at 3. The sum of we're gonna get to s sub infinity in a bit. We're gonna start with, well, what's s sub 1? It'd be the sum of the first 1 terms of this, which would just be 3. What's s sub 2? Well, it's the sum of the first 2 items of the sequence. And remember, this goes on forever. So it would be 3 plus 12. And we had a formula for this last time, but I'm just giving you an idea again about what partial sums are in the first place. S sub 3 would be 3 plus 12 plus 21. But what we've never really talked about is what's the sequence of these things, of these sums. This is 3, this is now 3 plus 12, this is 3 plus 12 plus 21. Yeah, I can do that in my head. And that goes on and on and on. And notice that's going to grow even faster, because not only are we just adding the next term, we're adding the sums of the first so many terms. Well, this one's going to go crazy. This one eventually is going to turn into infinity, of course. I mean, we know that turns into infinity. You started adding infinity. I sound like a playground kid again. Start adding infinity to infinity, you're going to get infinity. Well, of course you're going to get infinity. Anyway, that's what we mean now by infinite series. We're talking about the sum of all the terms as I'm talking about adding up an infinite number of terms. Well, in arithmetic series, it's really never any fun. It always goes to infinity anyway, so I'm taking my ball and I'm going home. The only one I really care about is things that seem to be convergent in the first place. If I have a convergent series, it might turn out that I can add them up, add up infinite terms of those, and I may actually have something I can deal with. I might have something that converges even as a sort of a sequence of these serial sums. Okay, you can tell I get excited about talking about this stuff. Okay, so first of all, let me talk you through this little string of delicious mathematics right here. What do I, if the sum of, I mean, you can read this. I've been saying this to myself over and over again to prepare myself for what I'm about to tell you because it's just too good. I don't want to mess it up. All right, if the sum of the first n elements of a sequence can be written this way: the sum of, as I goes from 1 to n, of all of the a sub I. So that's just what that means. That's basically what I was just doing right here. Here's a sub 1, here's s sub 2 really means a sub 1 plus a sub 2. S sub 3 means a sub 1 plus a sub 2 plus a sub 3. So if that's how I'm defining things, then the sum at infinity is the sum of all the a sub i's as 1 goes to infinity. So really it's just like adding up. It's like adding up. This whole thing here really came from 3 plus 12 plus 21 plus ... and it simply does not end. I'm adding this up onto infinity, which of course again here with an arithmetic series it's no fun. You know it's going to be infinity. But the sum of the infinite series itself is actually the sum of all of the terms. Okay. In other words, what I'm saying is I'm not adding 3 plus 15 plus 6. Sorry, I'm not adding 3 plus 15 plus 36. I'm looking at what these little strings are tending towards. Okay? Right, and that is actually the same as the limit, as n goes to infinity, of the limits of all of these little partial sums. So that's what I meant by this thing tending to infinity. I'm not adding these up. I'm looking to see what does this string start to look like when this list gets longer and longer. And that is really what I've written all out in symbols in here. Okay, that's what I'm saying here. I was typing up the notes here, and I sort of paused in my typing of the notes to explain to you the little pieces of what this meant. This is all in a box on page 516. They have a nice example with a flea named Fleance, but I think they misspelled it. They should have spelled it that way to make it more appropriate for the times. Anyway, she's a flea who's jumping around. They like to use this example a lot when they're talking about infinite series. You have something like, and this I'm going to edit it a little bit to make it match this whole idea of Zeno's paradox. Say you have to walk a certain distance. Say you're walking home from school, and your parents are asking, "Well, how come you're so late?" Well, to get from school to home, maybe you've heard this paradox before, and this is going to bother some of you, but remember this is the chapter that we're talking about. We're talking about sort of the philosophy of infinite things and that kind of stuff. The first thing you have to do is you have to get halfway there. Right, and it might take you half the time, but you're gonna go. First thing you're gonna do is get halfway there. Say this is like number line. We're going from 0 to, well, I don't even know how far home is, but we're gonna call it 1 for now. Like all the way home is one of these distances. Then after you sort of take your first Fleance jump, your first segment of this trip that takes you a certain amount of time, you're gonna spend half that amount of time getting half as far after that. So now we're sort of at 3/4. I've taken a half plus a 3/4. So I started at 0, and then I added a half, and then to the half I added another quarter, and now I'm at 3/4. Whoops, that's a quarter. And to that, over the next Fleance jump, we're going to go half the remaining distance, and that's going to keep going. And at this point on the number line now, I'd be at 7/8 because I've just added an eighth. I think you see where this series is going. And then I go half the remaining distance, and I'll be at 15/16. And now I need a smaller pencil. So I'm adding a 16th. Etc. And I'm going to keep on adding these up, and eventually I'm going to add 1 over. If you look at this little sequence, this is 2 to the first power, 2 squared, 2 cubed. The first one was 2, yeah, so I can actually just call this 2 to the n, and it'll work out. But I'm going to keep on adding that up for infinity. And if I'm adding that up, notice the sequence I wrote up here, these little numbers, this is not the same as this. This is actually those sums. The first one was half, the second one was 3/4, the third one was all of that, the fourth one was all of that. The question is, what's this whole thing going to go to as a big added up list of things? What's this sum as I keep adding these fractions over and over and over again? Well, I think without too much convincing, I don't know, maybe it would take a lot of convincing, but eventually you're going to get home. And eventually you're not going to, you're going to get as close to home as you ever want to get. Would you ever actually get there given this paradox? Well, that's why it's a paradox, and it's a classical paradox from math history. But we're not actually talking about whether or not you ever get there. We're talking about the idea of a limit. And the limit is that, yes, when you add up all these things, the limit of this series, the limit of adding a fraction on and then adding half of what's left, half what's left, half what's left, half what's left, keep going on to infinity, you're going to get super, super, super huge over super, super, super huge plus 1. Eventually, that limit of this sum now turns into 1. The limit of this fraction, I mean, this little fraction here is eventually going to, I mean, the limit of the sequence, half, quarter, 8/16, limits of the sequence here is going to be 0. 1 over 2 to the huge is 1 over a huge number, and 1 over a huge number is going to eventually turn into 0 at a limit sort of stage. But as I add those up and I keep adding those little tiny jumps and those little tiny fractions, the sum of where we've come from all the way to there all together turns out to be 1. Isn't this awesome? I love this stuff. Okay, if you could. Okay, so what's not interesting about any of this stuff is arithmetic sequence, arithmetic series. Because if you think about an arithmetic series, like that first one we did back here, arithmetic ones are always going to do this. They always have this sort of slope, kind of, you know, constant increase or even constant decrease, that always have an end behavior that is, you know, tail up or tail down, and it's always going to go crazy towards infinity already, even by itself, even in the terms. So as I start adding up more and more terms, it's just going to go to infinity even sooner. Of the geometric ones, some of them tend to sort of converge, like some of them converge that way, some of them converge this way, so they have a limit that exists somewhere. And sometimes it's 0, sometimes it's slightly different. Some of the geometric ones, I'm graphing a bunch of stuff on one graph, kind of do have end behavior that goes kind of crazy, but every once in a while you get a geometric one that actually converges at some sort of target. That means there's at least hope for this type. If you have some crazy positive or crazy negative divergent series of geometric series where as we go down the list the numbers start to get huge and huge and huge, then you know as you add those up the sum of that is just going to go on crazy. So it's not any fun. But and by fun I mean, you know, it doesn't even exist. But the ones that converge, the ones that actually have a limit, there's a hope there that maybe we'll get something. Now this isn't even geometric, but we'll hopefully get. There's a chance that we might get some limit that actually sort of slows down and sort of magnetizes around some certain number. Well, in general, this is too hard to sort of prove or state for like the ones where I had 1 over 2 to the n, like I was just doing. But for geometric ones, we can kind of settle this down and talk about when is it going to go crazy and when is what is the infinite series going to actually converge and exist. If we're talking about geometric series, the whole thing in general, the explicit formula is this, right? Each term starts to do this kind of thing for every g sub n. This g sub 1 isn't affected by however big n gets. This is affected by however big n gets. We always get r to some huge power being multiplied by the original term. And as this gets bigger and bigger and bigger, well, this will start to explode if you have a huge value of r. In the book, they say that absolute value of r has to be greater than 1. It's like saying r is bigger than 1, so we're talking about exponential growth. So of course when you graph that, that's going to go forever. If r is less than -1, you get that one curvy thing that starts to do this, where you have the first term's negative, the second term's positive, the third term's negative, because you keep multiplying by a negative number, so it keeps flopping. So it kind of has this double divergent situation here. So that's no good. So if r is greater than 1 or less than -1, I keep multiplying over and over again by 3, I get this huge thing, or by -3, I get that. But if I get if I get a value of r that's actually less than 1, or between -1 and +1, I'm going to get a graph. That's when I start to get these convergent series that start to do that, or this, and there's hope for that. Algebraically, I can show that if I'm multiplying over and over again by, oh, I don't know, a half or something like that. If that's the constant, multiplier, like 28 plus 14. Sorry, I'm saying plus because I'm thinking series already. The next term is 7. We had this one in a do now. 3.5. There's hope that this thing may actually converge. That when I start adding these, and actually this starts to look like the fiance thing. When I start adding these things up, that they will add up to a sum that will have a limit itself. And on page 519, they actually go through the algebraic argument. Again, I'm almost out of time on the video, and I said this is going to be a light section anyway. They go to the trouble of proving that, yes, in fact, whenever that ratio is in there, when it's an exponential decay situation, you can actually find the infinite series, and it's this. So, plugging those things in for the series we were just talking about, and you may have guessed this, we're kind of like halfway to 56, and then a little bit farther towards 56, and we're going half the distance remaining, that this one, if I plug this into that formula, I actually find out that the limit of the infinite series is 56. See you in class.